A 397 billion parameter model just ran on an iPhone, not a video of one, not a phone talking to a server somewhere. The device itself generating text with the network off. It used about 5.5 gigabytes of memory to do it. The model is nearly 400 billion parameters. That gap should not be possible, so here is what actually shipped. A project called flash-moe, written in C and Metal. Metal is Apple's graphics layer, the part that lets code speak straight to the chip. No Python, no frameworks, just handwritten code and hand-tuned graphics kernels. It runs a model called Qwen 3.5, and that model has 397 billion parameters. Parameters are the adjustable numbers a model settles on while it learns. Picture them as dials. Everything the model knows lives in where those dials are set. Nearly 400 billion of them. On an iPhone 17 Pro, it generates about 0.6 words a second. On a MacBook Pro with an M3 Max, it manages 4.3. On a newer M5 Max, it reaches roughly 13. Simon Willison, who has been documenting this field closely for years, wrote the whole thing up back in March. Now, this is a mixture of experts model. Hold on to that phrase because everything else depends on it. A mixture of experts model is one enormous model chopped into many small specialist subnetworks. The specialists are called experts. Every time the model handles a single piece of text, a routing layer picks a few experts to wake up. The rest stay asleep. This model has 60 layers, and every one of those layers holds 512 experts. 4 of them fire per piece of text, plus one shared expert that fires every time. Which means that of 397 billion parameters, about 17 billion are ever doing work. Read that again. 96% of the model is idle at any instant. So here is where the obvious explanation falls apart. The natural assumption is compression. Somebody squeezed 400 billion parameters down into 5 gigabytes. That is not what happened. Every one of those experts still exists at full size. Together they take 209 gigabytes. They are just not in memory. They sit on the storage chip and they get fetched while the model is thinking. And here's the part that makes this a story rather than a stunt. Apple published this idea almost 3 years ago. In December of 2023, a team of Apple researchers put out a paper titled LLM in a Flash. Kayvan Alizadeh, Iman Mirzadeh, Mehrdad Farajtabar, and 5 colleagues laid out the entire approach. Keep the model in flash storage in the same chip that holds your photos. Pull only the pieces you need into working memory on demand. They described 2 specific tricks. One reused the parts that had just been active, betting they would be wanted again. The other bundled data so the chip could read it in long continuous sweeps instead of scattered nibbles. Their measured result was 4 to 5 times faster on the processor and 20 to 25 times faster on the graphics chip. The press understood exactly what it meant. In December 2023, the headline said Apple had found a way to run large models on iPhones. Then almost 3 years passed, and no phone shipped doing it. So why did it take this long? The answer is not that everyone forgot. It is that the paper needed something the models of that era did not naturally have. The whole method rests on one condition. Only a small slice of the model can be needed at any moment, or you end up hauling the entire thing off storage anyway, and you have gained nothing. In 2023, the big models were dense, meaning essentially all of the model participates in every word it produces. Researchers had ways to coax sparse behavior out of them, but they were coaxing. They were fighting the architecture. Mixture of experts models do not need coaxing. The sparseness is the design. 4 experts out of 512 is not a trick applied to the model. It is what the model is. So Apple wrote the method for a world that had not arrived yet. The architecture caught up, and the paper was sitting there waiting. So here's the trick that finally made it work. The model gets split into 2 piles. The first is the dense core, the parts that steer everything, including the routers that decide which experts to call. That core stays in memory permanently, and it is about 5.5 gigabytes. The second pile is everything else. 209 gigabytes of experts sitting on storage, repacked so that each one occupies a known, fixed position. Because the position is known in advance, fetching an expert is exactly one read instruction. No searching. The reads fire in parallel, several at once, while the graphics chip is still busy with the previous layer. Per piece of text, the system pulls about 1.7 gigabytes off that storage chip. Every single word costs a gigabyte and a half of reading. It works because the drive in a modern Mac moves roughly 17 gigabytes a second. And then comes the finding that genuinely surprised me. They built a custom system for keeping recently used experts close at hand. Then they deleted it. Throughput went up 38%. It turned out the operating system's own ordinary file handling did the job better than anything they wrote. Left alone, it kept about 71% of what was needed. Their own name for this principle is blunt: trust the operating system. But they tried the opposite too. Handing the whole file to the system to manage as one mapped block, which is the textbook approach, ran 5 times slower. Predicting which expert would be needed next made things 18% worse. A small trained predictor for the same job got it right 31% of the time, which is worse than simply guessing based on recent history. The repository lists 58 discarded experiments. That is what real engineering looks like written down. One more piece. 45 of the 60 layers use a form of attention with a fixed size memory rather than a growing one. Normally, the longer a conversation runs, the more memory is needed to hold what has been said. In those layers, that cost stops climbing entirely. So now the honest part, because the framing oversells in several places. Start with speed. It processes 0.6 words a second on the phone, but you write faster than that by hand. So a single paragraph would take several minutes. Nobody is replacing anything with this today. Then storage, and this is the real wall. 209 gigabytes of experts at the standard setting. Squeezed harder, 120. Even the smaller number is more than most phones hold in total, and it has to sit there permanently. So the memory problem got solved. The storage problem replaced it. Worth sitting with that for a second, right? A phone that could run this would be a phone with almost nothing else on it. Every app you own is competing with a model you can barely use. There is a physical cost, too. Reading a gigabyte and a half off storage for every single word is sustained work for the hardware. All that reading draws power and it makes heat, and phones respond to heat by slowing themselves down deliberately. Nobody has published what happens to that 0.6 words a second after 20 minutes of it. That number is a sprint, and nobody has timed the marathon. And squeezing harder costs you. There is a standard way to score how confused a model is by ordinary text, where lower is better. At the normal setting, this model scores 3.6. Squeezed down to save space, it scores 5.7, which is a large fall. The project's own notes say plainly that at that setting, it breaks structured output and tool use. So the version that fits is not the version that works. And this is also a proof of concept, not a product. There is no App Store download here. A separate project called Swiftlet is chasing exactly that. And it has a 35 billion parameter model running inside a real iPhone app today at roughly 1 word a second. 35 billion, not 397. The distance between a demonstration and something you would actually open is still real. So strip the hype away and here's what changed. 3 assumptions broke at once. The first, that the size of a model decides how much memory you need. The second, that your phone was permanently a thin client, a window onto somebody else's computer. And the third, that the frontier of this technology would stay in buildings you will never enter. Getting the next part wrong will cost you either money or accuracy. If you want quick, reliable answers and you are not troubled by your text leaving the device, nothing here beats what you already use. If your work must never leave your hands or must run with no connection at all, the thing that was impossible 2 years ago is now merely slow. Slow and possible is a different category from impossible. And notice which way this is moving. Every part of this got easier in the last 12 months, not harder. The same code that crawled on an M3 chip runs 3 times quicker on an M5. The phone that could not hold the file this year will hold it in a few. None of that requires a breakthrough, it only requires the ordinary drift of storage getting cheaper and chips getting quicker, which has not stopped in 50 years. Now, a couple things to watch. There is an unresolved argument running between these projects right now. flash-moe deleted its custom expert handling and got faster by trusting the operating system. Swiftlet built a careful bounded pool instead and reports that its size barely matters either. Same problem, opposite answers, both shipping working code. But nobody has settled it. Another thing to watch is storage, not memory. Memory was the wall everybody talked about for 3 years and it fell. 200 gigabytes of experts is the wall nobody was talking about, and it is the one still standing between this and the phone in your pocket. Apple wrote down how to do this in 2023 and then did not do it. Somebody else did, on Apple's own phone using Apple's own paper. The number to remember is not 400 billion. It is 4. 4 experts awake, 508 asleep in every single layer. A model that is almost entirely unconscious at any given moment, thinking one small thought at a time. That is what ran on a phone, not a smaller model, a mostly sleeping one.